All right, so we are now moving on to bonds line structures and formal charge. All right, we talked a little bit about formal charge in chapter 1. I told you we're going to spend some time talking about it. Now it's that time. Okay, so a carbon atom we know will have 4 bonds when it does not have a formal charge. When a carbon has a positive charge, it is referred to as a carbo-cation. Carbo from carbon, cation from the fact that it's got a positive charge. When you have a carbo-cation, that carbon has 3 bonds and 1 empty p orbital. When a carbon has a negative charge, it's referred to as a carb anion. A carb anion will have 3 bonds and a lone pair, so no empty orbitals on a carb anion, okay? And this is always the case. If a carbon has a positive charge, that means it always has 3 bonds and 1 empty p orbital. If it has a negative charge, it always has 3 bonds and 1 lone pair. Formal charge affects the stability and reactivity of molecules. So you must be able to identify formal charges in bond-line representation. Okay, the following structure that you see below or above my head is incomplete because it doesn't have formal charges correctly indicated on atoms that have it. Formal charges must always be drawn in bonds-line structures. Okay, so let's fix the structure by adding them. We're going to do one together. Okay, so looking at this oxygen that I have highlighted in a box, what is the formal charge? Okay, let's go over that formal charge equation again. Formal charge equals valence number minus, in parentheses, lone pair electrons plus number of bonds the atom has, right? Oxygen, we know, has a valence number of 6. Okay, we can figure that out real easy from the periodic table of elements. This oxygen has 1 lone pair, so that's 2 lone pair electrons and 3 different bonds. 2 bonds to carbon and 1 bond to a hydrogen. So plugging in the numbers, we would get 6 minus 2 plus 3, or 6 minus 5, which equals 1. The charge on this oxygen is plus 1. Formal charges must be drawn always, but drawing lone pairs is optional and they are often not included in bonds line structures. This means you may need to be able to do the formal charge equation backwards in order to figure out how many lone pairs are on an atom. And again, we're going to do an example. Okay, again, let's look at this oxygen right here. Okay, no lone pairs drawn out, but we see a formal charge of -1. So using my formal charge equation, I'm going to plug in -1 equals valence number minus lone pair electrons plus number of bonds, all right? -1 equals 6 minus X, whatever the lone pair electron number is, plus 1. If I solve for X, I would see that I have 6 lone pair electrons or 3 lone pairs. And that is what we have around that oxygen, okay? By knowing the formal charge, the presence or absence of lone pairs is implied. Now, just like with carbon, we will see bonding patterns that will always be the case with oxygen. A negative charge on an oxygen means the oxygen has 1 bond and 3 lone pairs. No charge means that this oxygen has 2 bonds and 2 lone pairs. And a positive charge means that the oxygen has 3 bonds and 1 lone pair. Similarly, we see a pattern for nitrogen, which will always be the case. A negatively charged nitrogen has 2 bonds and 2 lone pairs. A neutral nitrogen has 2 bonds and 1 lone pair. And a positively charged nitrogen has 4 bonds and no lone pairs.